Yes, questions before we start. My intention today is just to complete the proof that we had started, the derivation that we started on Monday. But if you have any questions, of course, we can also discuss those questions first. Now, if you remember, what we were discussing on Monday was we had this matter, this material, and we were looking at the electric field inside this material. First, of course, we need to define what we mean by the electric field inside the material, because basically the electric field inside the material will be quite highly fluctuating. I mean, you might be very close to an electron, let's say, there will be an electric field in one direction, and at a very nearby point we'll have an electric field, will be close to a nuclei, where you will have another electric field pointing in a completely different direction. Now, those very large fluctuations is not really something we can actually measure in most circumstances, and they're not most of the time what we are interested in. What we are actually interested in is kind of an average electric field in a given region. So what we do is, for example, if you take this point, the point R, when we are talking about the electric field at the point R, what we are actually talking about is kind of an average electric field, which we define as, we just assume a small volume around the point R. Let's call that volume V prime. It is small compared to the macroscopic size, but nevertheless it should be large compared to the atomic size, where the fluctuations in the electric field occur at the atomic length scales. So if you just change your point at the level of an atomic size, the electric field will be highly fluctuating. And this we define as the integral of the electric field over this volume V, and divided by the volume V prime. And of course, okay, this is the average. So when we first have to evaluate the electric field, what is the electric field at the point R, and then take its average. Now the electric field will be due to, one, the charges inside our volume V prime, and also due to the charges outside our volume V prime. Now we had to treat them separately, because at least for the charges outside our volume V prime, we know that we can just use the dipole approximation and take an approximate value, dipole multiple expansion, and then obtain some value. For the charges inside our V prime, we cannot use that approximation. We cannot use the multiple expansion. We have to use some other means. And so we separated this into two parts: the electric field created by the charges inside our volume, plus the electric field created by the charges outside our volume. And then the average of the electric field, the quantity that we are interested in, is the average of this E in over our volume plus E out over our volume. And we had seen that the average of E in, assuming we have a spherical volume, this turned out to be minus 4 pi over 3, the dipole moment at the point R, where this dipole density at the point R we defined as over our volume V, over the volume that we are averaging, of d cubed R, let's say R prime, rho of R plus R prime, R prime, 1 over V prime, kind of the average dipole density in that volume. This was our definition of this P. And we were having some problems about how to interpret this E out, and that was where we had, we eventually identified our problem, but that's where we had left. So today I intend to pick it up from there and calculate the average of the electric field created by the charges outside my volume. Now this is defined as, well, the average is defined as d cubed r prime E out r plus r prime. Well, in this notation, what I'm doing is the E out r plus r prime is, okay, so I have this volume around R, the sphere around the point R, so the coordinate of my points relative to this point R, I denote them by r prime. And this is equal to 1 over V prime d cubed r prime over the volume V prime of that quantity, and that quantity is d cubed r double prime, such that let's write it as outside, or this r double prime is out of my volume V prime, of the charge density times, let's say we are looking at the electric field at r plus r prime due to a charge is located at r plus r double prime, divided by its magnitude cube. So that integral, that r double prime integral, is basically the electric field created by the charges outside my volume V. Do you agree? Now let's do a trick. Well, in fact, let's do the same trick that we did in the case when we were calculating the average of E in. I will change the order of integration. So this will be 1 over V prime, the integral of d cubed r prime outside, times the of rho of r plus r double prime, because that only depends on r double prime, it doesn't depend on r prime, times the integral of d cubed r prime r plus, well, let me write it in this form, r prime minus r double prime divided by r prime minus r double prime cube. And this is over V prime. Now that's an integral that we had seen also in the case where we were averaging E in. Remember, that is r prime minus r double prime divided by r prime minus r double prime cube. This is equal to minus d cubed r prime, r double prime minus r prime divided by r double prime minus r prime over V prime. But you see, this expression is nothing but the electric field created by a uniform charge distribution in V prime. The electric field is created at r double prime. Do you see it? Yes, no. So this corresponds to, we have this volume V prime, and r double prime is some point over here. This is uniformly charged because here we have rho is equal to 1. If it was not uniformly charged, we should have included the rho over there. It's uniformly charged. It's the electric field created at this point, but we already know what that electric field is. This because since we are out of this sphere, the sphere just behaves like a point charge. So that integral this is equal to minus, what is the electric field at the point r double prime? Hmm? 1 over r double prime squared in the r double prime direction. Not completely. What is the charge? The charge density is 1. V. V prime. Do you agree? Okay, so we are back over here. We have this quantity that we are trying to evaluate, which is nothing but E out, the average of E out, the electric field created at the point R by the charges outside our volume V, which is given by this integral. And we said that this is equal to, well, V primes, they basically cancel. Or let me just write it down, V prime, the integral outside of d cubed r double prime rho of r plus r double prime, that integral which we had just said that it is minus V prime r double prime divided by r double prime cube. Do you agree? So this V primes also cancel. We are left with minus an integral over the outside charges, d cubed r double prime, rho of r plus r double prime divided by r double prime cube. But you see, this is nothing but the electric field created by the outside charges at the center of V prime. When we take the average, we basically obtain the electric field right at the center. Do you agree? No. Hmm? So do you agree that the average of E out over our volume is equal to this result? So let's look at what that result means. So we had this volume V prime. This is at the R. So we have some charge densities outside. So we take a very small volume over here. That point is, this is the R double prime. So this is the coordinate R. So this point is basically at R plus R double prime. So the total charge of that volume is the charge density at that point multiplied by d cubed r. So I have this dq charge over here. It will be creating an electric field at this point. And the electric field created at the center of the sphere will be, let's say, dE. It will be rho r plus r double prime d cubed r minus r double prime hat, minus because the electric field will be in this direction, divided by r double prime squared, or this is rho plus r double prime d cubed r with a minus sign r double prime vector divided by r double prime cube. This is the electric field created by that very small volume. And when I sum them up, I obtain this integral over here with the minus sign. So, well, this is kind of an interesting result in its own, I should say. So whatever charge distribution you have outside a given sphere, if you take the average of the electric field over the volume of the sphere, this is a sphere. It doesn't work for any other volume. But for a sphere, the average of the electric field is equal to the electric field at the center. This is always true. So kind of, we are having these two interesting results. On one hand, if you take a sphere, whatever the charge distribution inside the sphere is, that charge distribution inside the sphere will create an electric field, and the average of this electric field is always equal proportional to the dipole moment of this sphere. Then we have the electric field that is created by the outside charges. Again, whatever the charge distribution of these outside charges are, the average of the electric field created by these outside charges over this sphere is equal to the electric field created by, again, these outside charges at the center of the sphere. Now we had this system. Well, at this point, let's say, this was our small volume, d cubed r. This was the position of the center of the sphere. This was r double prime. Now we have this localized charge distribution over here, let's say, which creates an electric field at the other point, at a faraway point. Typically it's far away. So we can make the dipole expansion. So the dipole expansion of the electric field will be basically dE will be equal to dq, the total charge of that sphere, divided by, let's write the potential, divided by r double prime. This is the monopole term. Then we have the dipole term plus the total dipole moment, that r double prime divided by r double prime cubed, plus other corrections. This is the potential. This is the potential created at this point due to this small charge over there. If we take the minus the gradient, that is the electric field. What's the gradient with respect to? With respect to r double prime or r minus r double prime? You see, if we had put the origin over here, then we should be taking the gradient with respect to the position of the center of my sphere, which is at minus r double prime. So it should still be with respect to minus r double prime. So if we write it as a gradient with respect to r double prime, there's a minus sign. So the electric field, the average electric field created by the charges outside is nothing but the electric field created at the position r by the outside charges. Remember, r is the center of our volume, which is equal to sum over all these very small volume elements of minus the gradient with respect to r double prime, minus r double prime, of dq is nothing but rho at the point r plus r double prime divided by r double prime plus p divided by d cubed r double prime is nothing but the dipole density at the point r double prime, r plus r double prime. So it is P, I just take the d cubed r double prime out. P at the point r plus r double prime dot r double prime divided by r double prime cube. Of course, this r double prime integral is outside my volume V prime. We agree? Let me make a change of variables. Rather than using coordinates relative to the center of my volume V, let me use the coordinates, the positions relative to the origin. So I will just define, let me call it some vector dd, no, not dd, I don't like. Delta. For the time being, I will change my notation later on. In this integral, delta double prime is equal to r plus r double prime. Note that in this change of variable in the integration, r is a constant. So d cubed r double prime is equal to d cubed delta double prime. So E out at the point R, the average is equal to outside d cubed delta double prime of minus the gradient. Now R, this is equal, R double prime is equal to minus R double prime is equal to R minus delta double prime. Now this gradient is with respect to R minus delta double prime of rho of delta double prime divided by delta minus R plus the dipole density at the position of delta double prime that delta minus R. Now hold on, I probably made a mistake over here. This is minus R double prime. Again, that is minus R double prime mainly because when we obtain this expression for the potential of a dipole, R is the position of my observation point relative to my dipole. So that is what R is. Now in this system, the position of my observation point is the center of my sphere, and its position relative to my dipole is minus R double prime. So that is why I have a minus over here. Another minus over here. So here I have minus R minus delta prime divided by R minus delta double prime cube. which is equal to minus the gradient with respect to r outside d cubed delta double prime rho of delta double prime divided by delta minus r plus p dot delta r minus delta double prime divided by r minus delta double prime cube. Now here what I used was the gradient with respect to r minus delta double prime is actually equal to gradient of r. Or we could have it as well written as the gradient with respect to minus delta double prime. But writing it as a gradient with respect to r is easier because I can take it out of the integral. Well, this is in fact what we could actually write this straight out without doing all these juggling of indices, etc. So you see we have some charge distribution outside rho. It creates a potential. The potential that it creates is the integral of rho over the distance from the position of the charge. And the distance is delta double prime minus r. The second term is just like we have some dipole density. Dipole creates a potential at the point r, and the potential created by that dipole is the integral of the second term. So the total of those integral, the two of those terms, is the total potential created at the point r. Now we can talk about the gradient with respect to r. The problem before was, since we were writing everything with respect to the origin with respect to r didn't seem to appear. So, but in this form, at least when we shift to the absolute coordinate system for all of the coordinates, then the dependence on r is apparent, and we can write as a gradient with respect to r. So that kind of almost completes our treatment. Now we have an expression for the average of the electric fields created by the outside charges. We also have an expression for the average of the electric fields created by the inside charges. And if we just combine them, the average electric field at the point r is nothing but minus 4/3 pi times this polarization density at the point r minus the gradient of the outside charges, d cubed delta prime, rho of delta double prime divided by delta double prime minus r, plus the polarization density at delta double prime, r minus delta double prime divided by r minus delta double prime cube. So this is the total electric field we have. Well, there's still something not that nice about this expression. You see, we have that integral over there. So to evaluate that integral, we have to specify some volume, we have to take some spherical volume, etc. But that is not something we want. I mean, we want some expression that doesn't depend on our choice of volume for our averaging, because the averaging shouldn't depend on our volume anyway. So we should somehow try to get rid of that restriction on our integral. Let us look at these terms. D cubed delta double prime rho of delta double prime divided by delta double prime minus r, minus the gradient. This time not outside v prime, but inside v prime. Let's see what this integral is. So basically I'm asking the question that, okay, that integral is an integral over the outside of my volume V. What if I remove that restriction? How much does my integral change? What's the change in my integral? So this is equal to d cubed. Well, let me change the notation. Just rename the dummy variable to r again. Rho of r double prime R double prime over R double prime minus R over the volume V prime. Now I will be doing a couple of tricks. One is I will replace rho by its average value. So since I'm replacing everything with the averages, I will also do the same thing with rho. And furthermore, since I'm replacing rho with its average value, and the V prime integral is a very small volume, the average value of the charge density doesn't really change over this volume. So basically, rho is a constant over this volume. Well, if I assume that rho is a constant over this volume, this is approximately equal to rho of R double R, which is, as I said, is just the average value, which is constant over my volume V prime, of the integral of d cubed R double prime of R minus R double prime divided by R minus R double prime cubed. Now remember, in this coordinate system, V prime is a sphere around the point R. So this is the point R. This is my V prime. Well, it's that integral, just like before, I can say that if I were looking for the electric field created by a uniform charge density at its center, that would be the integral that I will be evaluating. What is the electric field created by a uniform spherical charge density created at the center? Zero. Well, that basically tells me that at least in this first term, I can remove that outside restriction in the integral. I can evaluate that integral of the first term over all the volume of my material, not just the outside. Now let's look at the second one. Now the second term is minus the gradient with respect to R, d cubed R double prime, rho at R double, no, P at R double prime, multiplied with R minus R double prime divided by R minus R double prime cube, which is equal to d cubed R double prime P of R double prime gradient of, no, well, this integral we had evaluated, I don't know, just 2 weeks ago. Rizal was asking it. We will do basically the same trick. I will assume that P is constant. So this is let me forget this gradient for the time being. This is equal to, P is just constant. P is not constant, but again, I do the same trick. I replace P by its average. Well, P is by definition an average. It was an average since the beginning. But the V prime is a very small volume, so P changes to mostly over a very small region. It doesn't change, so I can just take it out. This is integral over v prime. What is this integral? Yeah, it's the same as the previous integral, right? No, there's something wrong I'm doing here. Okay. Is equal to this one. First, let's stick with this one, then we will review how. Okay? But if this is true, my claim is that it is true. Well, let's see. Okay, if I remove the constraint of the integral being outside my volume v prime, I don't add any contribution from the first term. The contribution that I add to the second term is exactly equal to this first term over there. So this sum this is actually equal to minus the gradient with respect to r of d cubed r double prime rho of r double prime divided by r minus r double prime plus p at the point r double prime r minus r double prime divided by r minus delta cube r double prime. Now this time this is an integral over all of the volume, not just outside. And this is our electric field for inside matter. As we expect, the charge density that we put has some contribution to the electric field, plus if the material is polarized, this P is the polarization of our material, that also contributes to the electric field. Okay, now the only step missing is this one. Now, if you have any questions, we can discuss them first and then go back to this result. Is it true? Well, let's give a 10 minutes break if you want, and then we can continue.